Hello, welcome to our final project presentation for ECE 6775. I'm Cynthia, and joining us is Angelica, Nikhil, and Nikhil, and we'll be talking about from Allo to XLS. Today we'll give you an overview of our project building two different compilation pathways from Allo to Google XLS. One pathway is a traditional compiler backend with structured lowering. The other pathway is an agentic LLM workflow that translates and iteratively repairs. Together, we'll study the strengths and limitations of deterministic compiler passes versus agent-driven synthesis. Building compiler backends for accelerator DSLs is extremely costly, and Allo needs flexible portable backends to target new hardware. Something we're interested in is the question, can LLMs automate the pattern matching aspects of backend construction? Let's start with an overview of Allo. It's a Python embedded accelerator designed with explicit constructs for scheduling and shaping hardware. One key gap is that there is no target backend for ASICs, which is where XLS comes. XLS is Google's open source hardware synthesis toolchain. In XLS, you can write your code in DSLX and the compiler will generate synthesizable RTL for ASICs. XLS supports two main execution models. The first is functions, which represent feed-forward computations, and the second is procs, which lets you express concurrent stateful hardware.
Our system has two branches. On the left, a conventional compiler backend lowers Allo to DSLX and to XLS-IR. It also detects systolic array patterns and builds proc networks. On the right, we use LLM agents that take Allo snippets, generate DSLX, and then run XLS tools to get error traces to iteratively refine the result. The DSLX lowering translates imperative MLIR, full of load stores and mutable memrefs, into pure functional DSLX. For example, stores become nested update expressions, and loops become functional for expressions with explicit accumulator variables. We first build an AST that preserves structure, then serialize it into actual DSLX code. Here's an example of a 4x4 matrix multiply in Allo that is customized to split the inner and outer loop in half and then reorder them. As one can see, this is faithfully carried out by the backend, generating the DSLX on the right. You can see the use of functional loops and updates to express what was done with imperative mutation in Allo. We also wrote a version that goes directly to the more regular XLS-IR. XLS-IR is SSA-based, flat, and purely data flow oriented. Unlike DSLX, it has no loops, so we must fully unroll every affine loop. Memrefs become flattened arrays requiring explicit index linearization. Because the IR structure is extremely uniform, we emit instructions directly during a single MLIR walk, with no AST phase. Here's that same Allo example, and on the right we have the beginning and end of the much more regular looking generated XLS-IR. Next, we handled systolic arrays. Allo expresses systolic arrays at a high level, but XLS expects a network of communicating procs. We pattern match MLIR to recognize systolic tiles, extract loop bounds and connectivity, and generate a full DSLX proc network. Here is the multiply accumulate PE kernel in Allo, as well as the proc that receives inputs and multiplies the multiply accumulate in DSLX. Each PE is stateful and uses blocking receive and send operations connected by directional channels. Here's the systolic grid generation in Allo, and the corresponding DSLX code to spawn procs for each PE and connect them with north to south and west to east FIFO channels. Our compiler evaluation starts with feed-forward gem kernels, which test the basic functional semantics our lowering pipeline needs to support. We tested different sizes and applied a suite of Allo transformations: baseline, outer and inner tiling, two-level tiling, loop reordering, and composed transformations. Across all variants, our DSLX lowering executed correctly under the source interpreter, and the generated XLS-IR also validated successfully, both with handwritten test cases. This shows our lowering can handle complex control structures and the functional update semantics needed for XLS. The second category we evaluated is systolic arrays, which require lowering Allo spatial abstractions into explicit proc networks. We generated arrays across multiple grid dimensions and for several data types, including floating point and signed and unsigned integers. All systolic configurations ran correctly under the DSLX interpreter, and importantly, the generated proc networks compiled fully through XLS's scheduling and Verilog cogen stages, producing synthesizable RTL. This demonstrates that our backend handles both feed-forward kernels and structured, stateful accelerator patterns.
The second thrust of this project examines the usage of an LLM agent-based system to automate the generation, validation, and refinement of Allo to XLS lowering. This exploration is motivated by the widening adoption of LLMs and growing interest in its applications. Our work developed a full LLM-based lowering system from Allo input DSLX output, metrics for comparison to manual lowering through traditional compilation techniques, and an analysis of the optimal configuration of LLMs for this task. Varied parameters include the model, the context provided, and the number of iterations for refinement. We focused on GPT models from OpenAI and Claude models from Anthropic. Our code rests on LangGraph and LangChain, two open source frameworks for building LLM applications. LangChain is a general purpose framework providing modular components for building AI applications, while LangGraph extends LangChain to enable stateful agents using graph-based architectures. Together, these frameworks allow us to develop a modular, organized agentic system. The diagram on the right shows the blocks that compose our workflow. The first block of the flow is the generate block, which passes the prompt to the LLM and receives the output. The prompt consists of a system message, which provides the LLM with the task context, a user message, which tells the LLM to lower the given Allo input to DSLX, and additional instructions where we embed DSLX documentation. After the generate state produces the DSLX output, the interpret block runs the DSLX interpreter on the produced code to check for errors and dictate the flow accordingly. In the event of an error, the system goes to the loopback block. If the output is valid, the system goes to the done state to exit the loop. In order to facilitate improvement between iterations, the error in a given iteration is appended to the prompt that goes to the next. The loopback state handles capturing and storing the error. The idea is that the agent can iteratively refine by learning from its previous errors. Our system sets a maximum of 10 iterations through the loop before deeming the trial a failure. Lastly, the done state is where the system captures and logs the metrics for the run. The recorded fields include the success status, the number of iterations taken, and the token usage. These metrics help to quantify the ability of the agent to lower Allo code and provide an insight into the associated trade-offs. We created a small benchmark suite to evaluate our agent's performance, consisting of 6 Allo variations of 32 by 32 matrix multiplication. The first example is a naive implementation, while examples 2 through 5 apply various loop splitting optimizations. Lastly, example 6 involves decomposing the matrix multiplication into 2 subkernels, as shown in the code snippet on the right. For each of the 6 examples, we run 10 trials, where one trial consists of iterating through the agentic loop until a valid output is produced, or until we reach the maximum of 10 iterations. We have a test suite which consists of DSLX matrix multiplication tests that evaluate the functional correctness of the produced output. These tests do not assess whether the appropriate optimizations were applied during the lowering. We evaluate 5 LLM models, 3 models from Anthropic and 2 from OpenAI.
Here are the results for the 5 models. The columns numbered 1 through 10 are the results per trial, and because our agent takes an iterative approach to refine the output, each number in the square is the number of iterations the agent took for that trial. A green means that the agent output passed our test bench, a red is a failing output. So our input, Allo, actually has the function header allo_gem, and we also wrote our test case with the expectation that that is the generated function header. But sometimes the agent outputs a slightly different function header. In that case, we have to manually change it and rerun the test. So the blue square means that the output passed the test after we named the function header and reran the test, and orange means that it failed even after renaming. To the very right, we also have columns R and I, where R is the pass rate and I is the average number of iterations. One can conclude that Claude Opus 4.5 outperformed the other models with the lowest number of iterations and highest pass rate. HiQ 4.5, on the other hand, significantly underperforms its Claude counterparts. GPT-5 Mini also seems to perform better than GPT 5.1, which is interesting because 5.1 is advertised to be the OpenAI's best model for coding. We also observed that there are differences in the LLM outputs, and we'll give examples of the outputs for the simple Allo function with no optimizations. For Opus 4.5, for examples, we found that most outputs actually resemble the 2 forms shown on the slide, and even so, these 2 forms are logically very similar, and there are just minor syntactic differences. So for example, how a loop is declared, or whether or not to instantiate temporary variables, and we found very similar results for Claude Sonnet 4.5 as well. GPT 5.1, on the other hand, has more general variabilities, as shown on and 2 of which are shown on the slide. The one on the left is very similar to the Claude outputs, whereas the one on the right instantiated its own helper functions. So we observed that Claude's outputs has less variabilities, most of which are just syntax, whereas the outputs from ChatGPT are more logical and structural. We've also noted that Claude generated its own test cases as well as the DSLX function, but GPT did not.
So now I'll be talking about testing and evaluation workflow. We utilize multiple forms of verification, randomized differential testing, and value testing at each level in the abstraction. For randomized differential testing, instead of writing expected outputs by hand, we treat the compiler-generated implementation as reference and use XLS's quick check system to automatically generate randomized inputs and compare the LLM-generated code against the compiler version. The nice thing about this approach is that it's fully automated and highly scalable. We were curious to see timing and area results of our compiled times performing synthesis and place and route. Evaluating at the Verilog level, we did cycle-accurate simulations using Verilator. All these designs are on a 2x2 map mul. As you can see, the cycle count for the gems are the same. The systolic array had a larger amount of cycles, but I believe that's due to streaming and the time that it takes to set up. The timing reports are as follows. The critical path goes from the input register to the final multiply and a multiply accumulate chain. This makes sense as it performs aggressive unrolling to generate the Verilog, and the clock period is 4.06 nanoseconds. The area is 190 by 192 micrometers. There are a lot more combinational cells than sequential cells, which makes sense as all loops are unrolled. Most assignments result in being combinational. Claude generated optimized XLS has the same period and critical path, same area and power as well. The ChatGPT generated XLS has the same period and critical path, same area and power as well. And the basic XLS generated by chat has the same period and general critical path, same area and power as well. The manually generated systolic design has longer clock period, and from simulation we know this design takes more cycles. It has less power but more area, which would be nice for designs that require smaller amounts of power. Overall, we successfully conducted the manual lowering paths from Allo to XLS for a subset of gem designs, and we demonstrated the ability of our LLMs to perform lowering. In the future, we would want to explore different contexts and documentation provided to the LLM, add more Allo features, and explore further randomized testing and other evaluations. Thank you.